what I want to do is just give you an overview of the architecture of the G2 system and explain why we've done certain design choices. So what we have is we have the actual graphic engine, and it's QML, Qt based. So this is the thing that actually draws the stuff on the screen. This is the underlying implementation. What you'd see on the screen obviously would be, you know, a combination of knobs and buttons and dials or whatever, numbers. So this is what you see on the screen. Now the question is, great, I have this graphic thing, I can move the knobs and push buttons, but how does that relate to the underlying core functionality? How does this actually, when I push the button, how does it turn a light on and off or whatever? So in the QML world, what we've done is we've written the viewer component. It's called a viewer. And this actually drives this guy. And what the viewer does, he sets up the environment for this thing, but then it provides a connection out the end, and this is an internal connection in the computer. So this is what we call the QML viewer. It runs the files that you create, which are in QML and JavaScript, and then it talks to what we call an agent, a TIO agent. It's a pipe, it's an internal pipe in the computer in Linux. And what the TIO agent does, we think is very important. Well, let me just do I'll do the whole thing. So you got the TIO agent, and then it talks to an SIO agent, SIO. And this actually talks to the physical serial port. And that would go to the embedded microcontroller that's doing your underlying core functionality. This may look complicated, but I'll explain why we're doing it this way. First of all, the serial agent, the reason for this architecture is, again, divide and conquer. So what the serial agent does is it connects the physical, this is the physical layer to the logical input of the computer. And this sets the baud, for example, baud rate, and other characteristics of the physical line. Now you could replace this with a different protocol. For example, if you wanted 485, you wanted Modbus, Profibus, CAN bus, whatever, because on here you've got, this is the logical, this is the message interface. And how the message goes to the final guy, you don't really care from this side. So we've got a message interface, this is the SIO agent. Customers can change this as the protocol. This is an interchangeable part. You can put whatever you want for the particular protocol. For example, if this was going into a car, this would be a CAN bus interface, and the messages on this side of the barrier would be things like speed, RPM, whatever. They're the messages coming back that is interacting with the guts of the car. Then we have this translate agent, and the translate agent is, in my mind, very important, because what happens is at this level, on this barrier, what comes on this side are messages, but they're still very much low level related to whatever the microcontroller is doing. So for example, I'll give you a car example. What is coming across here might be simply a byte that says, or it says RPM, it's just R for RPM, and then maybe 4 digits, 1200. So it's really low level, it's very much specific to this. And trying to get the GUI to understand what this is, it doesn't relate to the namespace in the GUI. The people doing the GUI are all in terms of object-oriented namespaces of controls and indicators, whatever. Also, if you tied the GUI directly to this, they become tightly coupled. It's much harder to change this. So what we do is we have a translate agent, and what the translate agent does is take this low-level domain-specific stuff, not just domain-specific, but interface-specific information, and translates it. We have a translate file. The TIO agent takes in a translate file. translate.text. And this simply says, when you get a message R followed by a digit, so let me do this. So for example, you'd say R%D followed by a digit, translate it into, for example, RPM.value equals the number. Say, well, you go percent D, so you put percent D there. But long story short is it changes this into something that makes more sense for the GUI designer. What's great about this translate concept is it means that the definition, this API, the API for the underlying microcontroller, and these guys don't have to be in lockstep. They don't have to be one-to-one. So if this guy decides, oh, I want to add an extra digit here, or I want to change the physical format of the messages, the types of messages I get, you can, by just changing the translate table, you can use the same GUI. So we want to be able to, again, like I said, divide and conquer. I want to be able to change this if it's going from a push button to a slider to any different kind of I/O control. I don't have to change this guy's code. I can simply change the translate table that says, instead of button maps to this functionality, I can say slider maps to this functionality, or whatever I want. Again, the idea is that the GUI is independent. The implementation of the GUI, I can change this as desired for the users without having to force the embedded microcontroller implementation to change. Because you do this, you test it, you should leave it alone. You don't want to keep, Lord knows, you know, we have a rule: you open the computer, lose a day, install software, lose a day. Whenever you touch something, there's a good chance you're going to break it. So trying to keep things as stable as possible is a big deal, and the translate agent helps to do that. By providing this translate layer, it helps to keep this stable with it independent of GUI changes. So the internals of our G2 system, because it's got the viewer, the translate agent, and the serial agent, it might look a little complicated, but it's fairly easy to understand. It's more maintainable, and it does the divide and conquer. We think it's the right way to go, and the people we've talked to like it too. So again, what's nice about this is if instead of, for example, a serial port, you wanted to use go over Ethernet. So this would be Ethernet, TCP, IP. All the details of that are hidden from the TIO agent. It's just passing messages back and forth. It doesn't care what the physical characteristics are. So all the G2 products are running embedded Linux. But to be honest, you shouldn't have to worry about that. Our job is to hide that from you. So what we do is we ask you simply to write files in QML, which is this essentially Qt markup language. These are interpreted, and you also write in a file JavaScript. This can completely define the graphic user interface. Then what we have is on the embedded device, on our display module, on our graphic engine, we have something called a QML viewer. And what it does is it takes these files and interprets them to come up with whatever the display is. If you've got a meter, 12.34, some buttons, selectors, dials, knobs, whatever you want. These are all defined by the QML and the JavaScript. The QML viewer is the one that paints it on here and interacts with the outside world through the translate agent and the SIO agent. So the idea is, the actual implementation of it is, it's quite nice. So if you've got you're sitting at your PC, on the screen, you're designing your graphic interfaces, knob switches, whatever. What you're actually doing is you're designing it, and the output will be QML files and javascript.js files. Then once you're happy with the look and the feel of it, you can simply take these files, drag them over. So on your PC, you've got a file folder window, with files. So this is the display, the G2 display engine. You simply take these files. This display engine has a Samba server. It has a server, a file server, just like you have in Windows. So what you can, within the development environment here, Linux or Windows, you can have a file explorer, which is a window into the files on this display engine. So when you've finished designing this, you take these files, you drag them from, let me see if they're in a file, if they were in a file explorer here, you're looking at them. You take these, you drag them into here, it automatically puts it on the engine, you restart the engine, and then you have the thing you just designed, it's running on the engine. So that's the methodology of development.